So, why are we interested in mathematics at home? What kind of mathematics takes place in our houses? And are we at home with mathematics? Meaning, is it something that we're comfortable with? A lot of the time, mathematics is just something that we maybe have to learn when we're at school, and there may be some rare cases when we leave school that we need to use some basic maths. But are we comfortable with it, and do we recognize it as a useful tool for doing some analysis or some complex analysis to do with homes? What I want to talk to you first about is the variables and the numbers that we have in our home. Now, some of them are quite obvious and intuitive. The first example I'm going to give is the temperature. So we're all familiar with temperature. We'll walk into our home, and if it's too cold, we can set the temperature on our thermostat to whatever value we want. So we know what value this is, and maybe we don't know it directly, but our thermostat will be keeping track of that number, of that temperature number. It will turn on the boiler, the heating will heat up the room, and then we'll have the temperature set to whatever we need it to be. But there's so much more happening when we just set the temperature on our thermostat. So that temperature, that change in temperature near the radiators is heating up the air, and that's going to change the speed of air through the room. So that's another thing that's changing within the house. We've also got things like the cost of running a certain appliance. So we're all familiar with, the price of something to run. We're looking at price per kilowatt hours, and this is something that we pay more attention to now than perhaps what we did a few months ago because of the cost of living. So we do pay a lot of attention to a lot of different numbers in the home. But there's also some things and some numbers that we wouldn't give that much attention to, or we may not have given that much attention to. Things like the carbon dioxide level in the house. So if you've got inadequate ventilation in the home and you've got a large amount of people in the home, the carbon dioxide level is going to increase. But this is something which is not that easy to keep track of. We may feel its effects, and I'll talk a little bit more about that later on, but it's hard for us to track. And another thing I want to introduce now is another thing that we won't have considered that much. It's particulate matter. So particulate matter is just something that's in the air that's not meant to be there. It's not one of the main gases that make up the air that we breathe. And we categorize particulate matter based on its size. So we have three main groupings. We've got particulate matter PM10, PM5, and PM2.5. These numbers at the end just refer to sizes in microns. Now, microns are maybe not something that we're familiar with conceptualizing, but it's something that's very small. So, PM2.5, these are particulate matter in the house that we're interested in keeping track of, and these are things which are about 1/50th the width of a human hair. So, very, very small particles in the air. Very hard to keep track of in our homes. But why would we want to? Why do we care about, some of these numbers that I've just introduced? So some of them are quite obvious. The cost of running an appliance, the cost of heating. That's obviously going to affect how often you turn it on, and that's going to affect your well-being. If you're in a cold house, then you're probably not going to be as happy as what you would be if you were in a nice warm house. The knock-on effect is if you're always using your heating, you're using a lot of energy, so that's going to affect the environment. But we've also got the health. So the carbon dioxide and specifically the particulate matter that I just talked about, these can have adverse effects on your health. So there's something that we really should be keeping track of and keeping track how these things can be generated within the house. You may be surprised to hear that cooking can generate a large amount of PM2.5, which can have negative effects on your health. And also if you're having a large gathering in the house as well. A lot of the time, you may be indoors with the windows and all the doors closed. The level of CO2 in the room can quickly creep to high levels that can affect your mood, your concentration as well. So that's why we should care. Now what I want to do is introduce the university's Smart House, which is a home for collaborative research across the university with many different departments coming together to do relevant real-world research of things which are taking place at home. So what we have here is a lovely 2-bedroom house, which has got everything that you'd expect in a real house. We've got bedrooms, bathrooms, fully working equipment, so cooking equipment, washing equipment, everything you'd expect, with one key difference being that this building is inside the university. So it's a house inside a building, it's a living lab. But what makes it a smart house? So that was a house, this is what makes it smart. It's the tremendous amount of data that we have continuously being collected in this smart house. So all those variables I introduced on the last slide and more, we're monitoring these in every single room continuously over time to see how maybe running the bath affects the humidity and the temperature in one room, but then how that can spread throughout the house. We're seeing how the impact of one activity can impact something else. So a lot of data, and what can we do with this data? We've got many different options. The first thing we could do is just decide what do we want to look at. So we've got time history of all these variables that we've introduced and tracked in the smart house. This is the data from last month. So we're looking at what happened in a particular room of the smart house in October. The first thing I'm showing you here is just when motion was detected in a particular room. So don't pay any attention to the scale just yet, because we'll be showing 2 plots here. But we're simply showing when motion was detected either by somebody coming in or out of a particular room in the smart house. Then we overlay that data, or that motion detection, with information on the carbon dioxide level in that room. And what's interesting to note is we can see that when motion is detected, we see spikes in the carbon dioxide level. And that's what you'd expect. When people are coming into the room, we exhale carbon dioxide, so the level is going to increase. We leave the room, that level is going to drop back to an approximate baseline value. But then we saw something interesting happen on the 18th. So we see a large spike which is significantly larger or significantly bigger than the other spikes we saw with the detection of movement in the room. So we had something interesting here, and this didn't happen again for the rest of the month. Now at this point we're not doing anything special, we're just looking at the data and we saw, okay, something happened here which is outside of the ordinary. It was up to us as researchers, or as just any human looking at data, to identify what that event was, and it simply was the fact that we had an open day at the university, so we had large groups of people in and around the house seeing some of the research we have going on there. But I think you can agree there's a lot more we can do with all this data. We've got a lot of different tools at our disposal. So we've got this big data. We could use machine learning and artificial intelligence. We could just do some pure mathematical modeling. We could do some statistical-based modeling, or what I focus on, computation and simulation. And we can tie all these things together to make what's called a digital twin. Now, we have already had a Discover lecture on a digital twin, and I'll invite anybody in the audience who's interested to scan this QR code in the blue head behind me, and that will give more detail on what a digital twin is and how we can develop digital twin technologies. I'll just provide an overview now for my talk. A digital twin is obviously something that's digital first, but it's linked to something that's physical, and in this case we're looking at the digital twin of a smart house. So we have the physical smart house, which is continuously feeding in sensor data to our digital model. So our digital model is continuously evolving and updating based on this sensor information. Then that digital twin can feed back to the physical model based on whatever rules we decide to implement. These rules could just be alerts, or they could be physical control to the house as well. It's really up to us how much two-way control we allow when we create a digital twin. What I want to talk about in a bit more detail as part of this Maths Week focused lecture is mathematics and simulation. And what we need for an efficient simulation, something that can, be useful to us in developing digital twin technologies. So the first thing is, the simulation has got to be based on something with real data. And we can check that off straight away. We've got all the real data from the smart house. It needs to be physics-based. Our model needs to be based off the governing laws of nature and able to give us some confidence in the prediction that the model gives. If we use machine learning and artificial intelligence, these things are a little bit abstracted. So we'd like to use something that's grounded in the laws of nature. It also needs to be efficient. So we could develop a highly complicated, a highly complex physics-based model which would give us a fantastic amount of information. But if this takes a long time to compute, it's of no use to us. We need this information and we need it as quick as we can. So the animation we're seeing here is actually an animation of the smart house where we're taking data from the radiators, just the temperature data, and turning that from 4 data points of temperature to 1 million data points of the temperature everywhere in that smart house. And we're also seeing how that temperature change affects the speed of the air moving through the house. Now you may be thinking, this is probably something that's really hard to develop, a fast physics-based model that allows us to get reliable data based on whatever we're seeing in the smart house. I want to now spend a bit of time to talk to you about how we can get these models and how they naturally evolved from something quite simple. So what I'm going to be talking to you about now for a few slides is cellular automaton or cellular automata. Now this is a branch of mathematics which really started in the 1950s and it evolved into something very useful, which is what I use in my research. And this all starts from an idea based on a state or a number line of a line of possible states. So let me just first introduce a one-dimensional line. This one-dimensional line, as you can see, has white boxes and it has blue boxes, which we can call 0 and 1. We've got 2 possible states and an arbitrary one-dimensional line. And at this point you might be thinking, well, okay, it's all arbitrary. What can we do with this? Well, we could pick a point and decide how that's going to evolve or how that's going to change over time. And we may decide to do that based on the state of the current cell and the state of the neighboring cell, so to its left-hand side and to its right-hand side. So we've got 2 states and we've got 3 cells which can determine the future state of that cell. So with that simple configuration, we have 8 possible configurations. So either all of those 3 cells could be 1, all of these 3 cells could be 0, or some combination of 1s and 0s or blue and white boxes. And we can decide, based off whichever one of these states we have, what to do next. So that green node is going to update based on its value and the value of its neighbors. And we can choose that update arbitrarily. So we may decide that rule or that configuration of states gives us a new state which is equal to 0. Likewise, when we move to the next set or the next cell, we may decide that this specific configuration gives us a new state which is equal to 1. So after some initial arbitrary random state and some initial arbitrary rules, we get a new state. And we'll just show that new row of cells underneath the one that we just started with. And I think we'll agree at this point it's nothing exciting. We've been completely arbitrary with how many states we have, how many rules we apply, and what conditions we apply as well. But these images are generated from these rules. So these are actually animations that I will play in a minute. But from a simple rule that I'm illustrating on the left-hand side, we have all these states equal a 1 or a blue box at the next time step, and all these states, all these 4 states on the bottom left-hand side equal a white square or a 0 state at the next time step. So I'm going to show 2 animations here. One of them is the one-dimensional simulation, and the second is the 2-dimensional simulation. So the animation on the left, we're just seeing a one-dimensional array of blocks updating over time. Whereas on the right-hand side, we saw a 2D simulation where a cell was updating based on all the cells around it. So we increased the number of possible states and possible configurations because we've moved from one dimension to two dimension. In one dimension, we have a fixed number of rules that we can apply, and it's countable. It turns out, for a one-dimensional case, we have 256 possible rules we could apply, and different rules would give different geometric patterns, some of them visually interesting like this one, some of them not. It all depends arbitrarily on the rule. And the same in two dimensions. The only difference is, in two dimensions, the number of possible rules has increased dramatically. So something that's beyond countable, just from going from one dimension to two dimensions. So what happens when we take it further? Because obviously we live in a three-dimensional space. Everything's got width, depth, and a height with it. So now we've got more neighbors and more possible rules that we can apply. So we're seeing now a 3D case where we're applying, again, arbitrary rules, and we have some initial state and it evolves into something different, some interesting group of blocks. But the number of possible rules we could apply to this system is astronomically big. It's more rules that we could write down, and it's more rules that we could possibly consider. So how can we do something useful with this? Because in theory, it's easy for a computer to look for a rule and apply the next condition. That's what computers are good at. That's what they're really fast at. But if we've got too many rules and too many possible outcomes, then it doesn't matter how quick your computer is, this is going to take a long time. We can simplify things. And we can simplify things by bringing physics, real-world physics, back into the problem. So instead of having arbitrary rules, we can apply physics-based rules. And we can apply physics-based rules that are going to make sure the mass of the system remains the same, make sure that momentum is conserved. So quite technical sounding things, but this actually simplifies the model. So we go from something that was astronomically big to something that we have a solution for that runs quickly and is grounded in physics. So that's what we're seeing on the right-hand side, is a physics-based simulation that evolved naturally from this quite arbitrary trial and error mathematics to something which can now give us real-world information and give it to us quickly. So what can we do with that? So this ties back into what we talked about on the first few slides, all these numbers in the house. And we can use these fast models to make predictions. If we know what the carbon dioxide level is in the house, and we know the speed of the air and how it's moving in the house, we can use that to make predictions about how it's going to be in the future. These computational models, like I say, need to be fast. And these ones are faster than real time, which means we can get this information and we can find out what's going to happen in the future quicker than what it actually happens in the real world. So we can take some preemptive measures. We can use this for smart health updates. We can see what's happening in the house and how this could affect the health of the occupants and the well-being of the occupants inside the house based off the current conditions. Likewise with the environment, we're all familiar with smart meters and the ability to control maybe your heating or your lighting remotely. Well, the same thing can be done here with a digital twin, but we have more information to make better informed decisions. So we can tie everything together. We can tie the mathematics and these fast, efficient models all together to make our homes better for our health and our well-being and the environment in the future. And that's all I have to say, and I will invite you for any questions. Thank you for listening.
Okay, I think I speak for everyone. We now have definitely a different understanding of maths and how it's actually applied at home. That was a very, very interesting talk. Thank you so much for this, Frankie. So on the side of questions now, have you always known that you want to be a mechanical engineer?
Well, the honest answer to that is no, because I didn't always know, when I was younger at least, what a mechanical engineer was. But from an early age, I was always interested in mechanical systems, taking things apart, trying to put them back together, and then that curiosity led me to take engineering as a degree at university, and then the passion grew from there and continues to grow.
Okay, so the passion was at the point that you just wanted to put things together, you wanted to build things.
I wanted to take things apart and then try and build them back together.
Or just break them and fix them afterwards.
Hopefully fix them, yeah.
Yeah, that's a good solution. So at what point did you realize that your passion for engineering can turn into an actual proper career for you? Was there a deciding point, or did you just flow into that amazing work?
I think this is something that I'd definitely say I just managed to, flow into naturally. I joined university after finishing high school, where really my key strength was technology, design and technology, anything hands-on. And then I joined quite an open degree in that it was a mixture of mechanical, it was a mixture of electrical, because I didn't know, I knew I liked engineering, I knew I liked this, but I didn't know specifically what I wanted. So I kept my options open. Then I found, a branch of engineering I was interested in, which was computational fluid dynamics, this kind of research. And I managed to follow that path through with a PhD and then finally a research, and then my job now as a lecturer. So I've managed to find something I like in engineering and just flow into this career path.
Fantastic. May that be a lesson to all of you. You can become an expert in whatever you're interested in. So basically your work is very diverse. You're an engineer, you're a mechanical engineer who's now working in a smart house with focus on maths. So how did that happen?
That happened because mathematics just crops up everywhere. So this kind of mathematics, I really developed an interest for this specific type of mathematics during my PhD. But what underpins it is actually the research or the work I was doing as an undergraduate degree in computational fluid dynamics. After that, I learned about this kind of maths, this kind of fast, efficient simulations based on cellular automata, and it just continued from there.
Fantastic. So, in your work in the smart house, what's the most rewarding thing for you? What aspect of your work do you find most rewarding?
It's the fact that it's real-world work.
Fantastic.
So we're working in a smart house where everything we're doing in there, all the experiments that we're doing, all the computational models we're developing, or all the work we're doing in that smart house can have a real-world impact. We all interact with our homes in different ways, and we may not know what effect that has on our home or on our health, but the research we're doing here and the research we're doing in the smart house gives us that information, and it's rewarding because it's directly and it's obviously relatable to real-world applications.
Fantastic. You're helping people. You're solving one problem at a time. Hopefully one problem every day.
At a time.
We'll call it one problem at a time. So in your talk today, you spoke about collaborative work. How do you find collaborative work with other experts, and how do you all bring your work into the world of a smart house revolving around math?
Yeah, well, the example I'd really like to give there, because it's maybe not so much of an obvious collaboration or an obvious link, is the work we do with the games development school. Mm-hmm. So they're really good at developing, immersive environments, and we've obviously got the smart house with all this data, and we're managing to work together to make augmented reality models of this house where we can, visualize these models from, our perspective. We can put the virtual reality headset on, we can see all this data through the headset, see how the speed of the air moves through the house. It's quite an interesting link we have with the games school, because we're able to take our two strengths together and make something that's quite immersive and very useful.
Fantastic. And for all the gamers in the audience, that sounds like a computer game to me. That's all fantastic. So I think it's time that we open the questions to the public. Does anyone have any questions they would like to ask? Yes, please. So the question basically was based on the fact that the smart home is a building within a building.
Yep.
So obviously it's not quite real. So
yeah. So the question was, what can we do with that? We've not got, that real world data. I would answer that in the fact that it's kind of a strength as much as it's a weakness. We have controllability. So if the house was outside, we're subject to whatever the environment is outside. It could be raining, it could be sunny, it could be snowy. It could all happen in the same day here as well. We've got repeatability with the experiments we do. We know exactly what the temperature is outside. We know all these sensors I talked about in the smart house, they're outside of the smart house as well. So we know things like the temperature difference inside and outside of the smart house. We know the carbon dioxide levels inside and outside. So the fact that it does remain constant is actually a bit of a benefit in some aspects. We've got repeatability and control over everything we do.
Do we have any more questions? Yes. So the question is revolving around the spike about the slide where we saw the spike in the movement of air, and was there a correlation between the CO2 change and the movement of air?
All these sensors that we have in the smart house, they're movable, and a lot of the time if we're doing a test somewhere else in the house, maybe we want to do a highly detailed test in another room, we just take the sensor off the wall and place it somewhere else. So these sensors move around, so they're not always going to give an accurate prediction. If the sensor remained in the room, then we'd hope that trend continued, but yeah, we do move them around, so that's probably why there was a bit of a mismatch in the data there.
Okay. Any further questions? We have one from the live stream, I believe. Okay. So what role do data decision-making play in your world? In your work, sorry.
Yeah, well, the short answer to that is, all the data is in the smart house, and that just feeds into rule-based decision-making for whatever we want to do in the digital twin. So we'll have all this data which can feed into the model, but then it just boils down to a simple rule. How quickly is the temperature changing? Do we want to intervene in action, or do we not? So the data would feed into a predetermined rule.
Okay, fantastic. So if we have no more questions, I actually have one more for you. So can you please describe a specific project, basically, where a problem was solved by your mathematical skills, and that had a significant impact on the outcome of the project?
I think
you're not on a job interview, by the way.
So for that question, I'd say, look, mathematical skills, I don't want to pretend I'm a fantastic mathematician. I will say I've got a good understanding of some basic maths, which has allowed me to solve a lot of small problems. So it's the small day-to-day problems where I need to maybe find an expression for the change of an angle, or the expression for the change in volume, or something like this, where the mathematics isn't really that complicated, but it's having it at the front of my mind. I can call to it quickly, and I can solve small problems quickly to help develop these kind of models.
Fantastic. Lovely.
So I guess just to add to that, you don't need to be an amazing mathematician. These kind of models just developed from some quite simple mathematics.
Fantastic. And can you give us an example of a real-world application of the mathematical models or algorithms that you use?
I can give you an interesting one. So
Lovely.
These models are based on something called the lattice-Boltzmann method. They're mesoscale computational fluid dynamics models. This time they're applied to a house. And obviously everything in the house is a real-world application, like what we said. But the same exact model it can be used for anything that we want. So I used these models to look at inkjet printing.
Okay.
So I was looking at modeling inkjet printing for the fabrication of printable electronic devices. So it was another real-world example that's completely different to the one we've just done, but it just shows the versatility of modeling and mathematics. It all depends on what you want to do, but the underlying theory's the same.
So you mentioned inkjet printing. Would you like to give us a bit more insight in what that actually is?
Well, that's the multi-phase modelling.
Oh, so that was the blue slide.
Yeah, we have we have multiple fluids, so we've got liquid and air. In that example, I was looking at how a droplet would interact with a surface, how it would evaporate, and then how whatever was inside that droplet would be deposited on a surface. So same type of modelling, the exact same type of modelling, but a completely different application.
Fantastic. Once again, Frankie, thank you so much for your insightful talk today. As I said, I think we all learned a lot about smart homes, how mathematics is applied, and how integral it is actually of our daily life. Thank you so much for coming. Thank you for everyone who's attended the live stream, and I hope you have a lovely rest of your day. Thank you.
Thank you. Thank you.